All right, so what we're going to do in this online lecture is we're going to advance the basics of indifference curve analysis. What we're doing when we do indifference curve analysis is really a form of constrained optimization. But you can really think of economics this way. We have some constraints. We face scarcity. We can't consume absolutely everything that we would like. Right? But we also have preferences, right? So we would like to optimize. We would like to get the most out of life that we can. So we face constraints, but we try and optimize within those constraints, right? And so we're going to move into consumer theory, where we look at the consumer as doing constrained optimization. Now, when we have this constrained optimization, what we're going to do is we're going to think about the idea that often we don't know what a consumer's utility or their preferences or their desires actually are. I mean, we can kind of map them out and we can give an estimate, but one thing that we do know quite well is the constraints that they face, right? Utility, we're not really sure exactly what somebody's utility function would be, or what their indifference curve would be, or what their preferences are, but we do know that preferences are somewhat stable. We assume that they're relatively stable. They're not changing all that often, and we can give a basic approximation of them, right? So what we're going to do often in economics is leave those preferences, leave those utility functions, leave those indifference curves, leave the desires of the individual constant, but then we're going to see what happens when we tweak the relative price ratios. When we tweak the relative price ratios, what we're doing is we're changing the constraints. We're changing how that consumer is actually constrained in his action towards his desired ends. Right? This is the major tool of economics, to look at how a changed budget constraint, or how a changed constraint to someone's desires will impact outcomes given their preferences. So we'll look at how relative price changes can change behavior. Okay, so the first thing that we're going to do is we're going to ask the question, how can we represent this budget constraint if we have two goods, X and Y? B is our budget constraint. It's going to represent how much money we have to spend on those two goods, X and Y. So what we have to do is we have to say, well, the total amount of money that we have, our budget constraint B, has to be equal to our price of X multiplied by how much X we are actually going to consume. So if we spend some money on X, we have to say, well, how much money total did we spend? How many goods did we get multiplied by what was the price? But then also we have to say, okay, in addition to that, we also have to consider that there's another good Y, and we have to do the exact same thing. We have to say, well, our total budget will be not only the price of X multiplied by how many X we get, but also in addition to that, the price of Y multiplied by how much Y we consume. So here we have our budget constraint in mathematical form. If we want to take it out of mathematical form, we can do a little bit more math to kind of do our thought experiment to see how we can take it from the math to a graphical form, right? So here's the thought experiment that you want to do, is you want to say, what if we spent no money on one of the goods, okay? So to move from the mathematical form to the graphical form, that's a great thought experiment to go through, okay? What if we spent no money on one of the goods? So let's say we spent absolutely no money on Y. Okay, so let's turn this into a big old goose egg 0, and let's leave the rest of the equation the same. So we still have B is equal to the price of X multiplied by the quantity of X plus 0. Okay, so this would be a case where we had our budget constraint and we knew we were going to spend absolutely nothing on Y. How much X could we then consume? Well, we can figure that out, right? So what we can end up doing here is we can isolate our QX to be equal to our B over the PX. Okay, And so now what we have is we have an equation form where if we spent 0 on y, we can think about, well, what quantity of x could we actually consume? Well, you might think, well, who cares? We just rearrange this equation. But often, if you think about this, we'll often know what our budget constraint is. How much money do we have to spend on things? And we will also often know what the price of a good actually is. So if we know B and we know the price of X, we could know the quantity that we would consume of X given that we had no spending on Y. Now we can also do the other side of this and say that, well, what if we spent nothing on good X? What if X was 0, right? We could go through and we could reduce down for our QY. We could say, okay, well, QY is equal to our B, how much money we have, the budget we have, over the price of Y. And again, we often know this side of the equation, so we could have the answer for Q. So if we zeroed out one of the variables, this is what we would end up having. This really helps us understand how to construct a budget constraint graphically. There's 2 key points on a budget constraint graphically, and they're both cases where we either spend 0 on X or we spend 0 on Y. So when making your budget constraint from a mathematical equation, that's the thought experiment you have to go through. So if you know the total budget and the price of both goods, we can actually map the constraint. We can figure out the extremes by looking at the case where if y is 0 or if x is 0, figuring out our values for x and y, and then starting to put them on the graph and connecting them with a solid line. So what we can do is we can say, okay, let's pretend if y is 0, we know that qx equals b over px, right? And so we can fill in. We can say, oh, if b is 50, if px is 5, and if py is 10, we can fill into these equations. So here what we have is we can figure out qx when y is 0 by plugging 50 in for b and 5 in for px. So what we end up with is a qx of 10. Okay? And then we can do this for if x is equal to 0, right? So if x is equal to 0, we have 50 over 10. And then we can say, well, our qy then would be equal to 5. So here what we have is if quantity of x is 0, so when x is 0, our quantity of y, our y, will be 5. And if the quantity of y is 0, our quantity of x, or x, will be 10. We can now plot these points and start our graph. Okay, so putting it together to start our graph, if we look at, we were given a budget constraint of $50 if our budget is 50, and if the price of x is 5 and the price of y is 10, we saw that if y was 0, x would be 10, and if x is 0, y would be 5. So what we can do is we can go through and plot these points. So if y equals 0, so if we go up 0 on the y-axis, right, we have to go over to 10 on the x-axis. And then we can say if x is 0, so we go 0 over on the x-axis, then our y is equal to 5. So we have these 2 points. With the linear relationship that we have here, we can go through and we can just connect these 2 dots, and that is our budget constraint. Now you might say, hey, that was a lot of math to get to where we're getting to, but you do want to be careful. A lot of people will look at this and they will say, oh, well, the price of x is something like 10, and the price of y is something like 5, right? Which actually the opposite of that is true, okay? So you do have to be a little bit careful here. Do the thought experiment. If we got 0 y, if we spent 0 of our money on y, how much x we could get, and then that will tell us the quantity of x that we could get given its price. So as x gets cheaper, right, as the price of x goes down, we actually move further out this way. Sometimes people misinterpret that and they say, oh, x gets more expensive, and then they move x out. If x is getting more expensive, we would actually be moving x in. Seems stupid, seems like an easy, kind of silly mistake to make, but people make that mistake all the time, so watch out for it and kind of think through this math as to what we actually did here to draw up the budget constraint. Now we can make a straight line between these 2 points to give us the budget constraint, but another thing to keep in mind is what the slope of this straight line is. So our budget constraint will have a slope of px over py. And we can see this if we go through, if we start at y equals 5, if we think about this, px over py, the price of x over the price of y. Well, in our example, the price of x is 5 and the price of y is 10. So we have here 5 over 10 or 1/2. That's going to be the slope of our budget constraint. So if we start at y equals 5 and x equals 0, and our slope is 1/2, what we're going to do is we're going to go down 1 over 2. So if we go down 1 and over 2, we should end up at 4, 2. So we have 4 units of y and 2 units of x. So that would be a bundle of goods that we could afford to consume. If we think about it, if we were at 4y, and y is $10 a piece, that would be $40 on y, and 2x, that would be $10 on x, so we would have $50 having been spent, and we would have our budget of $50 completely spent, okay? And you could keep going from there. You could go down 1 more, and over 2, and here, as opposed to having the 4 on the y-axis and 2 in the x, here now we have 3 in the y-axis and 4 in the x, right? You could keep going through, down 1 more, takes us to 2 and 6, and then down 1 more, takes us to 1 and 8, and then down 1 more, takes us to 0 and 10, right? So we can see that makes up our budget constraint. That entire line is our budget constraint. It's represented by the slope of price of x over price of y. So next we're going to say, how does the consumer behave given these constraints? We're going to model this consumer behavior with what we call indifference curves. These indifference curves are really just a mapping of one's utility functions, okay? There's some basic things about indifference curves. 2 basic utility indifference curve concepts that we have, 2 major assumptions that we really want to focus on here is, 1, we like variety, okay? And the fact that we like variety, that we get diminishing marginal utility from the consumption of something, is going to give us the curve of indifference curve. It's going to give us that curved shape towards it. And the second assumption that we're going to use is going to be that more is preferred to less, okay? And more is preferred to less is going to help us interpret this graph here in this situation. So let's break that down. We'll return to the diminishing marginal utility and the curve of the indifference curves in just a minute, but let's look at the basics of an indifference curve. We have both goods, y and x, and we're going to plot the utility that we get from these different combinations of the goods, right? Anything along the curve we're indifferent between. So points A and B both will give us an outcome of a utility of 10. So we're indifferent between those 2. Now we said more is preferred to less. So if we can move to the northeast of a point on this indifference curve, right? If we can move in this direction towards the northeast, say at some point like point D, right? We know that we're going to be better off. So any indifference curve that we find that's further out to the northeast is going to be better off. And then point C, we can say we know is worse off. We don't know what level of utility, but we know it's lower than the level of utility of 10 because it is not to the northeast of where we're at. So we're moving to less preferred as we move down to the southwest. One thing that's really important to remember, especially for your future studies with indifference curves, is that there's an infinite amount of indifference curves, okay? We just plucked out a few where we labeled some points, A, B, C, and D. But the reality is that there's an infinite amount of indifference curves. They all exist, but when we draw up an indifference curve, what we're doing is we're just isolating one of those curves and saying, this is the relevant curve for our current analysis. But all of those other indifference curves still exist. So if we isolate out point B or the indifference curve AB, right? That doesn't mean that, hey, if our budget constraint or something changed, we couldn't reach some different level of indifference curve, right? This is just mappings of utilities where our preferences leave us indifferent between the consumptions of X and Y. So there's this infinite number of indifference curves that exist out there. We just graph one or two of them to show them as ones that are especially relevant right now, given the constraints that we face in the situation that we're in. Another thing that's a characteristic of indifference curve that's kind of obvious is that indifference curves can never cross. Okay, they can never cross. So if you look at J1 on our green indifference curve as compared to M1, you would say, oh, M1 must be better off. But if we move down here, the pink line that contains M2, right, shows M as being worse than J. Well, if these curves are supposed to represent things that are indifferent, we can't have these things flip-flopping, the relationship between J1 and M1 and J2 and M2, right? So you can go through and prove this to yourself, but you can just kind of see, well, this is a certain level of utility. It can never simultaneously be higher and lower than this level of utility. So it doesn't work to ever have utility curves for one individual crossing. So now what we can do is we can combine our budget constraint with our indifference curve, and we can talk about optimization, right? So we can draw up our budget constraint, and then we can draw on an indifference curve, and we can say, okay, where is this consumer optimizing? We're going to assume that the consumer is thinking more is preferred to less. So his behavior will stop when he has optimized within the constraints that he faces, right? So constrained optimization here. So we can go through and we have an example indifference curve and budget constraint drawn up here. The budget constraint is fixed, but there's an infinite number of indifference curves. Is this the relevant indifference curve, right? We'll call it indifference curve I, right? Is indifference curve I the relevant indifference curve for a consumer who's optimizing within his constraints? Well, if we can think of any point that would make us better off than either points A or C, we're not at the relevant indifference curve, right? And now, why wouldn't we be at any other point along the indifference curve other than A and C? Well, at any other point along A and C, we're either below our budget and have some more money to spend, or if we're up here or out here, we're above our budget and we can't spend that much money. So we're constrained by the budget constraint. So if we can move to the northeast from this indifference curve, we make ourselves better off. What could we do? Well, we could move this indifference curve a little bit further this way, right? And we could see that we would be better off. We'd be at a higher indifference curve. But as long as there's this little eyeglass kind of shape here, right? Is this eye slit shape, we know that there's room for us to move and move and move our indifference curve further and further out to the northeast. So we're going to keep moving that indifference curve out, 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 and out until it just touches at one point. When that indifference curve just kisses the constraint, when you have indifference curve J here, we move out to this point where point B is just this kiss between the constraint and the indifference curve. Only then have we optimized. At that point, we have no option to move further to the northeast, where more is preferred to less, because we're limited by our constraints. All right, so here we have optimized. So this is a huge point within optimization theory, intermediate microeconomics in general, that when the constraint kisses the curve, that's when we've optimized. Okay, to think about the optimization point and some of its characteristics, we need to know a couple of things. First off, we need to think about the slope of a curve at a particular point. So if we have that particular point, let's call it point B, our optimization point, right? What's the slope at point B? Well, we can look at that and we can say it would be the rise over run of this point. So we can kind of draw kind of a line that's just tangent to this point. That would give us the rise over run, right? The slope of this situation, how much y changes versus how much x changes, right? That would be the slope on this curve at that point. So we have, at that point, we have the y over x, the rise over the run. That line is just tangent to the curve. That would give us the slope of that curve. Let's go back to thinking about if we're at an optimization point, either A or C, when the indifference curve is below the budget constraint. Okay? When we think about the slope of the curve, think about point C here. The slope of the curve at point C is what? Well, we could draw this tangent C to our curve. And that's the approximate slope of our curve at this point. The rise over the run. How much y changes with a change in x. So we can see that slope of this kind of pink dashed line is not the same slope as the maroon budget constraint. Okay? But if we move out to our optimization point, point B, where our indifference curve is optimized, if we're at that optimal utility curve, right? If we think there, well, what's the slope of the indifference curve at that point, point B? We would say, okay, well, it's this dashed line that's just tangent to point B. Well, guess what? That dashed line is exactly the same as the budget constraint. What that means is that the slope of the budget constraint is equal to the slope of the indifference curve when we're optimizing. That's a neat property that gets used a lot in economics here. We can see that the slope of the indifference curve, which is going to be our what we call our marginal rate of substitution, is equal to the slope of the budget constraint, which is our price ratio. So we know when we're optimizing, our price ratio must equal the marginal rate of substitution. So the slope of the indifference curve is the marginal rate of substitution. We write the marginal rate of substitution of two goods as the marginal rate of substitution, MRS, of x, y. Okay? What this means is how many more y's do you have to give up to get one more x? And in equation form, we can solve this through as the change in y over the change in x negated out. So we have a negative of the change in y over the change in x. All right? And that's going to be our marginal rate of substitution. Okay, so let's look at point B here and think about what is the marginal rate of substitution at point B. Well, what we do is we say, what's the change in y? And if we're at point B here, if we go through and we say, okay, well, let's go down to down 1 in terms of y and over to this point here. So let's say, what's the marginal rate of substitution? Let's change y by 1. Okay, so we have a 1 is our change in y, and it's a negative 1 because we decreased y. And let's go to this point here. Well, what would we have? We would have down 1 y and over 1 2x, right? So we'd have down 1 over 2. So down 1 over 2. So we have a change in x of positive 2. We have to make this negative. So our marginal rate of substitution is 1/2, right? Which, what does that mean? It says how many y's do you have to give up in order to get one more x, okay? Well, at this point right here, at point B, we have to give up a half y to get one more x to leave us indifferent. So here we have a marginal rate of substitution equal to 1/2. Now we can also look at point A. So for the marginal rate of substitution of A, what we can do is we can go down 1 again. We'll do the same thing where we drop 1 in the y. We can see how far over we go in terms of x. So here we drop 1 and we go through. We can see that basically we only change about a half in terms of x. Right? So whereas before we dropped 1 and we went over 2, now when we drop 1y, we go over 2x. So plug that into our equation. We have a negative 1 change in y divided by a half change in x. But we have to make that negative. So what we end up with at point B is a marginal rate of substitution of 2. 1 divided by 1/2 is 2. So you can see on the same indifference curve, we actually have different marginal rates of substitution. And in fact, what happens to the marginal rate of substitution is that as we get more x, right? The marginal rate of substitution of xy, right? The marginal rate of substitution here is diminishing, which means the more x that we get, the further and further to the right that we have, the more that we are going to be willing to give up x to get just one y, or the less we value x relative to y, right? So here, x is valued more than y. 1/2 x is worth 1 whole y. Whereas here, as we've gotten a lot more x, 2x is worth 1 y, right? And so x in itself has diminished in how much utility we have. This is what gives us the curve of the indifference curve, that assumption of we like variety, or the fact that we have diminishing marginal utility.